Hello everybody and welcome to this A-level chemistry video about energetics. As you can see from the outline, there's quite a lot to cover in this video. So we will start by looking at exothermic and endothermic reactions. We'll move from there into defining what an enthalpy change is, and from there we'll look at some examples, specifically enthalpy of formation and enthalpy of combustion. We will then move on to Hess's Law and take a look at Hess cycles, the thermochemical cycles. And we'll finish by looking at mean bond enthalpies and tie that back in to both Hess's law and enthalpy change experiments. And because this is such a big topic, I've broken it up into two parts, and I'm going to release a second video about energetics where we will focus solely on the experiments that you carry out to measure enthalpy changes and their associated calculations. I want to begin our video by just defining a few terms that are involved in thermochemistry experiments. And thermochemistry is the study of heat changes during chemical reactions. And in fact, most chemical reactions do give out energy or take in energy as they proceed. It might be a small amount, and so that means it's not really perceptible to us if we're holding a beaker or touching a test tube, but there is likely to be an energy change value. And this will be down to, as we'll see later, chemical bonds being broken and new ones being formed, because energy has to go in to break old bonds and energy is released when new bonds are formed. So usually those two aren't the same amount, so there will be a change. The first example of a thermochemistry experiment that I want us to consider is an open system. The first type of thermochemistry experiment that we're going to consider is an open system. And in an open system, energy and matter can be exchanged between the system and the surroundings. And by the system, we really mean the chemicals that are reacting together. And the surroundings, in fact, really means the rest of the universe. And what we mean by energy being exchanged is literally an overall release of energy during this chemical reaction from the chemicals to the surroundings, or an overall taking in of energy in this reaction. So in fact, energy would go both in and out, but there would be an overall movement in one direction. And matter can also be exchanged between the system and the surroundings, in this case because my conical flask has an open top. So gases could escape out of the top of the conical flask, or they could move inwards. Again, on this occasion, they're unlikely to do both, but I'm showing a double-headed arrow to show that the chemicals could escape through the top or they could be taken in. The second type of experiment involves a closed system, and that's where we take our conical flask and we put a bung in the top. And this is a slightly simpler scenario because only energy can be exchanged between the chemicals and the surroundings, because there is no way for gases to get in or out to this system that is closed to the outside surroundings. And the final type of system that exists is what's called an isolated system, where our conical flask, probably still with a lid in fact, would be inside a separate container. So it is thereby completely isolated from the rest of the surroundings, and so neither energy nor matter can be exchanged between the system and the surroundings. Now, what I should say is that in A-level chemistry, almost every scenario that we encounter is going to be an open system. But I want you to be prepared for other eventualities, and certainly if you do A-level physics as well, you are likely to encounter the other different types of system. Now, you should remember from your GCSE chemistry that there are two different types of chemical reaction that involve heat changes. The first one is exothermic and the other one is endothermic. Now, exothermic involves a reaction that gives out heat as they proceed. And we can show this on our diagram in the same way as before by drawing arrows like this. And heat energy is exiting. Now what this means in a little bit more detail is that the chemicals have got less energy than they had at the beginning. And that makes sense because heat energy is being given out to the surroundings. What is a little bit trickier is the fact that this is registered by our thermometer as a rise in temperature. And this makes sense because heat energy has been given to the thermometer from the chemicals. And so the thermometer is hotter, and it is the thermometer that is measuring the rise in temperature as a result of this reaction. It isn't measuring the energy of the chemicals because the chemicals have lost energy. So because energy is being given out to the surroundings and the thermometer is part of the surroundings, it registers a rise in temperature. Examples of exothermic reactions include neutralization, where an acid and alkali react together, and also combustion, where fuels are burnt and the release in energy from the exothermic reaction is put to some further use, for instance, in a power station to produce electricity. Endothermic reactions, in contrast, they involve the chemicals taking in energy from their surroundings. So we can say that heat energy enters the chemicals from the surroundings. Now the thermometer is part of the surroundings, and so if the thermometer gives energy to the chemicals, the thermometer loses energy, and so we will see that the temperature drops in this experiment. Now, examples of endothermic reactions are a little bit more obscure. You will remember from GCSE level the thermal decomposition reactions, and thermal decomposition is where heat energy goes in to break bonds and to break substances apart. We've also got the treatment of sports injuries using cold packs. The physiotherapist would break a pack lightly, and then chemicals would mix together that would react in an endothermic reaction, taking heat energy away from the injury. And in fact, that reminds me of an extra example of an exothermic reaction, which is hand warmers that, again, you crack slightly and chemicals start to mix together and release heat energy. So overall, we have got exothermic, where heat energy exits, and we've got endothermic, where heat energy enters the chemicals. Some people remember it slightly unscientifically as endothermic because heat energy is going in. An experiment you will probably remember that demonstrates exothermic and endothermic reactions involves solid copper sulfate. If we get this left-hand test tube and we fill it with the blue copper sulfate that all of us will be familiar with from way back in year 7, this is known as hydrated copper sulfate and has got the chemical formula shown up here. Cu for copper, SO4 for sulfate, and then it's hydrated. And this dot is the water of crystallization. And what that means is when copper sulfate crystals form, one copper ion and one sulfate ion will combine with water in a ratio of 1 to 5. And so as the crystals form, water gets trapped in the lattice structure of alternating positive and negative ions, and 5 water molecules are trapped for every 1 ion of copper. Now, in this experiment with hydrated copper sulfate, you provide extreme heat using a Bunsen burner. You'd probably use the roaring flame, so let me just adjust this diagram accordingly. And what happens in this reaction is the water that was trapped in the crystals is released from the solid, and it will rise up out of the tube. It's no longer trapped as the water of crystallization. And you would probably notice this by seeing some condensation on the side of the tube. What you would definitely notice, though, is that the copper sulfate would lose its blue colour. It would happen gradually at first, starting at the bottom. It would turn white, and then you could, if you wanted to, stop with a layer of blue at the top and white at the bottom. But ultimately, if you continued, you would end up with white copper sulfate. And this type of copper sulfate is known as anhydrous copper sulfate, which is copper sulfate without any water. So copper crystals with water attached to them are blue, hydrated. Copper that has lost its water is anhydrous, and those crystals are white. If we were to turn this into an equation, we would need to balance it by adding the 5 water molecules that have escaped. Again, if we were to do this in a chemical reaction and write the equation, This reaction is reversible, and we show this by adding the arrows that look like this. One arrow pointing forwards and one pointing backwards. And this is very logical. If we have to heat the left-hand side to make it turn into the right-hand side, and that process releases water, this process can be reversed if you add this water back in. Now, it's impossible really to precisely add 5 water per copper sulfate on the way back, so you would get a pipette and you would add water in. What is easier to say, though, for sure, is that this left-hand reaction is endothermic, because it doesn't happen unless you warm it up using the Bunsen burner. And so it follows that when you add water to the right-hand side, this is an exothermic reaction. And this is the case for any reversible reaction that you will come across, that if one reaction is endothermic, the reverse reaction will always be the opposite type of reaction. And in fact, we can say with confidence that it will release the same amount of energy in the exothermic direction as it takes in the endothermic direction. Which is why if you were to do this experiment in a lab, you would not hold the test tube in your hand as you are adding the water to it, because it will get very hot. Not Bunsen burner hot, because there's water to take that heat energy away, but it still will definitely get hot, because lots of energy is being released. The amount of heat energy given out during a chemical reaction depends on the quantities of reactants used, and so the energy is usually measured in kilojoules per mole. So to combine these two terms, energy and quantity, so kilojoules and moles, we have a new term, and this term is enthalpy change. And enthalpy change is defined as the heat energy change measured during a reaction at constant pressure. So there's two parts to that definition. Enthalpy change is given the symbol delta H, and it is measured in kilojoules per mole. Now I've written it kJ mole minus 1, and that is the way that I want you to write it, but just for your understanding, kJ slash moles is the same units, so kilojoules per mole, kilojoules per mole. The to the minus function has the same significance as the forward slash does. So that's explained the units. I should explain the symbol. The symbol delta is the Greek letter for capital D, and it's used in science and in maths to mean change. You'll remember in other topics we've used the lowercase d, which looks like this, to indicate a partial charge or a partial change from neutral, to think of it as, again, being a change. So the Greek letter delta, the capital D, means change in this case, enthalpy. Now, the amount of heat given out or taken in by a reaction varies with the conditions, temperature, pressure, or concentration of solutions. And so what that means is, when you are measuring an enthalpy change, you need to say what conditions you were doing the experiment in. So for instance, were you doing this reaction under what is taken to be standard conditions? Or were the conditions different from standard? The conditions which are taken as standard are temperatures of 298 Kelvin, which is equivalent of 25 degrees C, which is normal-ish room temperature, apparently, although not in the UK, in my experience. A pressure of 100 kilopascals, which is 100,000 pascals, and that is atmospheric pressure, so that is 1 atmosphere, normal atmospheric pressure. And finally, and less relevant in year 1 chemistry, the concentrations of any solutions that we are using need to be 1 mole per decimeter cubed in order to be considered standard conditions. And so overall, when we are measuring an enthalpy change delta H, If we did our experiments under standard conditions, we use a circle with a line through. Looks a bit like the London Underground symbol. And so standard conditions, I'll just do it again over to the left, a line and then a circle. And that means standard conditions. And so the idea behind these standard conditions is that our chemical reaction will take place at constant pressure. That's all wrapped up in the definition of enthalpy change. So it would be taking place at 100 kilopascals of pressure. The temperature would begin at 298 Kelvin. It would change during the reaction because it's either exothermic or endothermic, but then it would return back to 298 Kelvin. And so we would see how much energy was given out during the warming up and cooling down of this reaction. And so by standard conditions of 298 Kelvin, we mean that that is the starting and end temperatures of this reaction when the reaction is considered to be beginning and to be over. We're going to return to exothermic and endothermic reactions briefly just to link them to enthalpy level diagrams. Enthalpy level diagrams, sometimes called energy level diagrams, are used to represent enthalpy changes. They show the relative enthalpy levels during a reaction. And so the y-axis has got enthalpy and the x-axis has got the extent of the reaction, which really is a fancy way of saying time. Because what they show is they show the amount of enthalpy stored in the reactants and the amount of enthalpy stored in the products. And on this occasion, the difference between the two is a negative difference. In other words, the amount of energy the chemicals have got goes down over time as the reactants turn into products. And this negative delta H, this decrease in energy of the chemicals, is for an exothermic reaction. This enthalpy level diagram is really similar for an endothermic reaction. We've got the reactants here and they gain energy and turn into products. And so we can see that the chemicals have gained energy. This is an endothermic reaction. The temperature will have dropped because the chemicals have taken energy from the surroundings, and this is a positive delta H. These enthalpy level diagrams, sometimes called energy level diagrams, are quite similar to the reaction profiles that you will recognise from GCSE level. The biggest difference is that we don't show the activation energy or the energy going in or out during the reaction, the hill, if you like, of the reaction profile. These just show a movement downwards for a negative enthalpy change and a movement upwards for a positive enthalpy change. We're going to take a look now at a few enthalpy change definitions that you need to know for A-level chemistry. First of all, the general name for the enthalpy change of any reaction is the standard molar enthalpy change of that reaction. And this is the symbol that this is given. Sometimes it is given a little subscript R afterwards, and that is referring to any reaction. So R is for reaction. The first specific commonly used enthalpy change that we're going to look at here is the enthalpy change of formation, usually shortened to the enthalpy of formation, and it is given the symbol delta H with a little subscript F and the superscript standard conditions. Occasionally you might see it written delta F H standard like that, but in exams by far the most common is this form. Now you actually have to be able to define the enthalpy of formation, and when you're defining any enthalpy change you should remember it, I think, in a particular structure. So first of all, it will always begin with the phrase the enthalpy change when, and I've put those three dots there because you're going to insert something specific here, and the definition is going to finish with the little phrase under standard conditions, because any enthalpy change is defined as something happening under standard conditions. Now, the specific enthalpy change that we're looking at will influence what is going to be written in the middle. And the enthalpy change of formation is when 1 mole of a substance is formed from its elements. And the fact that it's formed, that's why it's called the enthalpy of formation. Now, depending on the number of marks for this definition, that might be all that you need to write. If, however, it was a 2-mark question, you might be expected to add this, which is that all reactants and products need to be in their standard states. Now, that's particularly clear when we get an equation to hang this on, because I don't really like remembering definitions as sentences. I prefer to remember equations that illustrate the definition, and then I can work backwards to work out what my definition sentence needs to be. So an exam question might ask you to write an equation that represents the enthalpy of formation of water, H2O. And to do that, obviously, we need to know the definition, or we need to remember the core elements of the definition. And so obviously what we are making is water, H2O. And we're making it from its elements. And the elements in water are hydrogen and oxygen. Now, both of them are diatomic elements. If you remember from another video, the way to remember the number of diatomic elements and what they are is this little mnemonic here, which is I have no obviously brainy close friends. And that stands for the elements iodine, hydrogen, nitrogen, oxygen, bromine, chlorine and fluorine. Now, all of these elements exist as diatomic molecules, which means that they aren't single atoms, they go around in pairs, which is how we can remember that the elements hydrogen and oxygen are diatomic. So we are making our water from the elements hydrogen and oxygen. Now, I remember that the enthalpy of formation is when we need to have 1 of something. And so I would stick that 1 into the products, which is a little bit weird because normally we put multipliers in that are 2 or greater, but it's relevant here because it helps us remember what to do in the reactants. Because now we've got that 1 there, we know that we've got 2 hydrogen atoms in the products, and we've already got 2 hydrogen atoms in the reactants, so that's okay. But we've got 1 lot of 1 oxygen, so we've only got 1 oxygen atom in the products, which means we can only have 1 oxygen in the reactants, which means that the multiplier that we have to put in front of the oxygen is in fact a half, because a half multiplied by 2 is 1, and that gives us our balancing in there. And so because the definition of enthalpy of formation says that it is when 1 mole of a substance is produced, we may end up with fractions in our equation. And then the second part of the definition is that everything is in its standard states. So we need to go back to our equation now and add a little G for hydrogen gas, same for oxygen, and water is a liquid in its standard state. If we did one last example, which was the enthalpy of formation of ammonia gas, NH3, in the same way we know that we are making ammonia, and we know that it is a gas, and we know that because we're writing an equation that shows that the enthalpy of formation, we need a 1 in our product. And then we need to remember that we've got nitrogen, and nitrogen, as we can see here, is diatomic, and it's a gas, and we've got hydrogen, which we already know is a diatomic gas there. Then it becomes a case of balancing. We've got 1 nitrogen in our product, and so we need to have half an N2 in our reactants. We have got 1 lot of 3 hydrogen, so we've got 3 hydrogen in our product, which means we need 3 hydrogen in our reactants. So we could write 1.5 hydrogen. I don't have the space to do that, so I'm going to write the fraction 3/2 hydrogen for our multiplier. And so all of these equations must show that 1 mole of the substance is being formed. And as you can see, I've chosen 2 examples that end up with us having fractions elsewhere in the equation. One last thing about enthalpy change of formation, and that is the enthalpy change of formation for elements, for instance, O2 gas. Now, the equation for enthalpy of formation of something is where you make 1 mole of that thing from its elements in their standard states. And so the elements that make oxygen are just simply oxygen. And so what we've got is an equation where O2 gas is turning into O2 gas. Once we're happy that we've worked out the equation, we don't really need that 1 there. And so what this shows us is that O2 gas is turning into O2 gas. And since nothing is really changing here, the enthalpy change of formation is 0 for all elements. And that makes sense because when you are making something from its elements, if it's already an element and it's turning into the same element, nothing's really changing. And so there isn't going to be an enthalpy change there because everything has got just as much energy as it had before the reaction happened, but it's not really a reaction because nothing's changed. I realise what I've just said sounds confusing, so let's go back to the most important thing, that the enthalpy change of formation is 0 for any element. The second enthalpy change definition that you need to understand is the enthalpy change of combustion, which is given the symbol delta H for enthalpy change, a little subscript C for combustion, and the standard conditions symbol as well. And as before, this is the enthalpy change when something happens under standard conditions. And the enthalpy of combustion is defined as the enthalpy change when 1 mole of a substance, so once again we're underlining 1 mole because it must have a 1 in front of this substance, is completely burnt in oxygen, and again all reactants and products are in their standard states under standard conditions. Now I am putting this in red here as opposed to it being a consistent, this is always the case. So the definition for enthalpy change of combustion and enthalpy change of formation have got an identical second red line here. All reactants and products are in their standard states. This is not the case for the enthalpy changes that you need to learn for year 2 chemistry. So it is noteworthy that this second sentence is not uniform for all of them. It can definitely vary. But the most important one for enthalpy of combustion is this top row. 1 mole of a substance is completely burnt in oxygen. In other words, we are not undergoing incomplete combustion. And so for the enthalpy change of combustion of methane, which has got the chemical formula CH4, we are burning 1 mole of methane. So I'm going to put the 1 there, even though you wouldn't normally. And this burns in oxygen, so we need to have O2 in our equation as well, because oxygen is a diatomic gas. And then we're going to make the oxidation products. We're going to be burning these things. And so the carbon reacts with the oxygen to make CO2, which is a gas, and the hydrogen reacts with oxygen to make water vapour. Now, even though it makes water vapour, we write them in their standard states in this equation, so water needs to be a liquid. In our reactants, we've got 1 carbon atom. In our products, we've got 1 carbon atom, so this is balanced. We have got 1 lot of 4 hydrogen atoms in the reactants. In the products, we've only got 2, so we need to have this multiplier in front here, which gives us now 2 lots of 2 hydrogen, which makes 4. In terms of the oxygen, because it appears in 3 different places in this equation, it's best to leave that until the end and solve the other elements first for the balancing and then leave the oxygen to the end. That's the case for any element that appears 3 times, but it's most commonly oxygen where this is the case. So in carbon dioxide, we've got 2 atoms of oxygen. In 2 lots of 1 oxygen, we've got another 2 atoms of oxygen. So together, 2 and 2, of course, makes 4, which means we need the multiplier 2 in front of that. If we take a look at a second example, where this time we are burning the liquid methanol, we first of all need to write methanol in the equation with the state symbol L, and I would encourage you to get into the habit of writing the digit 1 on there. Now, of course, it's burning in oxygen. It's burning completely, so we're going to make carbon dioxide and we're going to make water vapour. And then we need to just look at the balancing. We have got 1 carbon, 1 carbon. This is okay. We've got 4 hydrogen here. We've got 2 hydrogen here. So we need a 2 there. And just as we had in the previous example, on the left-hand side, we need to have the same as on the right. So we have got 4 on the right-hand side. We've got 2 here. Now here is the pitfall to watch out for, which is why I chose this example. There's an oxygen in the methanol molecule. And so we've got 1 oxygen here. We need to have not 2, but we need to have 3. And the way we get 3 is we put 1.5 in front of the oxygen, or 3/2, oxygen gas. And that's this equation now done. Now, we mentioned completely burnt in oxygen just for your information. If we weren't to burn this completely, we wouldn't make carbon dioxide, we'd be making carbon monoxide, so that little 2 wouldn't be there. But for enthalpy of combustion, it must always be complete combustion. We're going to move on now to look at something that is often referred to by my students as the hardest bit of the energetics topic, and that is Hess's Law, which leads into Hess's cycles. First of all, Hess's Law is useful because it allows us to calculate enthalpy change for some reactions that can't be measured directly, because it allows us to use a more indirect approach. And what we do is we use enthalpy changes that can be measured to work out other enthalpy changes that can't be measured. A good example where this is the case is the reaction that we looked at earlier, where the anhydrous copper sulfate reacts with water and turns into the hydrated copper sulfate. It is really, really difficult to make sure that precisely 5 water molecules have hydrated each copper sulfate, as opposed to maybe 3 or 4 or something like that. It's really, really difficult to know that you have precisely and perfectly added each of those 5 water of crystallizations for each 1 copper sulfate. So getting that 1:5 ratio absolutely spot on is really hard to do. Now, Hess was a German scientist in the 1800s, and his law can be paraphrased to what I've got here. The enthalpy change for a reaction is the same whatever the route is taken for that reaction. Or to put it slightly differently, it only depends on the initial and the final enthalpy of the chemicals, or in other words, the enthalpy of the reactants and the enthalpy of the products. And so, if we create an enthalpy diagram here, and I hope you can tell that this is for an endothermic reaction, we can see that the products have got more energy than the reactants, so heat energy is going in. So what Hess's law tells us is it doesn't matter how many extra steps are taken in this reaction, the enthalpy change will be whatever this number is here, and I'm just going to make up a number and call that plus 50, because the products have got 50 kilojoules per mole more than the reactants do. But what Hess's law is telling us is that maybe the reactants don't turn straight into products, maybe they turn into an intermediate, and maybe this intermediate requires 70 kilojoules of energy to go in to form it, and then the intermediate turns into the product, and this releases 20 kilojoules per mole's worth of energy, and so the overall change is 50. Now that is exactly the same enthalpy change as if these chemicals had turned into another intermediate instead, maybe taking in 40, and then a new intermediate instead, taking in another 80. And then last of all, this different intermediate turns into the product, and that releases 70 kilojoules per mole. And so the overall change was that 120 went in these 2 steps, and then 70 went out. And so this is an overall change of 50. And so the key part of Hess's law is stating that it doesn't matter how many stops you take along the way. All that matters is the enthalpy of the reactants compared to the enthalpy of the products. A nice easy way to visualise this would be to think about money. So imagine you had £200 and I was to give you £40. Obviously now we know that you would have £240. Then I give you another £80 and that takes us to 320. But then I take £70 away from you and that brings us down to 250. And so in terms of a change, because you had 200 at the beginning and now you've got 250, the change, and remember that's what we care about, so I'll just use the symbol delta for change, is plus £50. And so it's the same idea for enthalpy change, only of course we're talking about heat energy per mole rather than about money. This relationship can be shown using Hess's cycles or thermochemical cycles. So if we just used R to represent the reactants and P to represent the products, the enthalpy change for converting the reactants into products will be equal to the same value as if we turned the reactants into some different intermediates before turning them into products. And so what a cycle does is it shows the main equation that we're interested in, and then it has coming down at an angle alternative reactions involving those same reactants. So let's turn this into an intermediate, I, and then let's turn that intermediate into the products. And so if this first reaction released 20 kilojoules per mole's worth of energy, and the second one released 50 kilojoules per mole's worth of energy, then we know that going straight from the reactants to products would equal the same amount. And so the way you use these triangles is very similar to how you would use vectors in maths. And so how we use these cycles in chemistry is we say, okay, I'm going to start here at the reactants, and I want to know what the energy change is turning the reactants into products. But I also know that the enthalpy change for a reaction is independent of the route. So converting the reactants into the products will release or take in the exact same energy as if we got there a different way. And so we're going around this cycle around an alternative route. So we're starting at the star and we're going to the intermediate, and then we're going from the intermediate to the products. And so what we have done is we've gone plus 20 down the first arrow, and we've gone plus 50 up the next arrow. And so the enthalpy change for this reaction is plus 20 plus 50, which is 70 kilojoules per mole. And this is the exact same concept regardless of how many steps there are. So let's have the same idea. Enthalpy change for this reaction is our unknown, but we do know a series of other changes. We can turn reactants into the intermediate W, then into X, then into Y, and then we can turn it into the products. And we know that the first change, R into W, has an enthalpy change of minus 20, and then the next one is plus 70, the next one is minus 30, and then the final one is plus 60. And so we use our Hess cycle to start at the bottom of the arrow that we're interested in, and we finish at the head of the arrow. And so we go all the way around the cycle to here, and all we do is we sum each enthalpy change that we passed along the way. So the enthalpy change for this reaction is minus 20 plus 70 minus 30 plus 60, which gives us plus 80 kilojoules per mole. This is made slightly more complicated if the arrows don't always point in the same direction. So suppose we can turn our reactants into products, but we can also turn our reactants into chemical M, and chemical M can also be made from chemical L, and chemical L can turn into chemical P, our products. And once again, we're trying to work out what the enthalpy change is for the reactants into products arrow. And let's say that R into M is plus 50, L into M is plus 30, and L into P is plus 40. This time, we're applying the same principle. We're starting at the bottom of the reactants arrow and finishing at the head of the reactants arrow. And so we're following the loop like that. And so we're going with the first arrow, and this is plus 50. And here is where our first difference comes in. We're actually going against the L to M arrow. And what's really important at this point is what I said earlier, that if turning L into M is plus 30 kilojoules per mole, then turning M back into L will be minus 30 kilojoules per mole. And that's what we're trying to do in the cycle up here. We're turning M into L, so this means we're going to have to flip the sign to minus 30 on this occasion. Then when we're turning L into P, we're going in the correct direction, so that's going to be plus 40. And so this time the enthalpy change for the reaction is plus 50 minus 30 plus 40, and so that's going to give us 60 kilojoules per mole for our final value on here. And if we wanted to show this without using any numbers at all, we can say that the enthalpy change for the overall reaction is equal to enthalpy change 1 take away enthalpy change 2 add enthalpy change 3. And that's because we're going against the arrow for enthalpy change number 2. So to sum that up, if you are going against an arrow, you must reverse the sign. So a positive number becomes negative and a negative number becomes positive. A slightly harder version of this question is if you are asked to create your own Hess cycle. Now, happily, these are really quite rare questions, which is just as well because they're quite difficult. But let me explain how you would do this now. So first of all, you will have to be presented with a series of equations through which you have to construct a Hess cycle. So the method to do this is to look for commonality between your equations. And if it's going to be a triangle, there will be commonality in 3 different positions. So first of all, we've got x turning into y. And so my recommendation would be to rewrite one of these equations in exactly the way that you're presented with. So x turns into y. And then look for commonality within the other equations. So in the next equation, we are shown that y can turn into chemical Z. So let's add that arrow on here, y turning into chemical Z. And then in the final equation, we're shown that chemical Z can turn into chemical X. And so let's add that on there, Z can turn into chemical X. And we're also given some data, so let's put that into the cycle now. X turning into Y, we are shown, is plus 50. Y turning into Z, we're shown, is plus 60. And so Z turning into X, that is the enthalpy change that we're trying to work out. And the reason I've organised it like this is to show you that you don't have to have the unknown chemical on the top of the triangle. It really doesn't matter which you put in which angle. What matters, crucially, is the direction that the arrowheads are pointing and how you use the cycle. So you always have to choose where you're starting correctly. So we're starting at the bottom of the arrow for the unknown, and we must always finish at the top of the arrow of the unknown. And so what we're saying is the value that we don't know will be equivalent to these 2 arrows, one after the other. And so first up then, we are going against the arrow of y turning into z. And so if y turning into z is plus 60, z turning into y, going the opposite direction, will be minus 60. And since x turning into y is plus 50, y turning into x will be the exact equal but opposite amount, which is minus 50. And so we're left with here the enthalpy change for our unknown reaction, Z to X, will be minus 60 add minus 50. So we're taking away 50 from minus 60, which gives us minus 110 kilojoules per mole. Now we're going to start using some real chemicals next, but I wanted to really make something clear here, and really I can't say this often enough, so I'll try and say it at least twice more. And when you are calculating the enthalpy change for a reaction, it does not matter what type of enthalpy change you are calculating. All that matters is the type of data you are given. So I'll say that again. The thing to pay the closest attention to is the type of data that you are being given to use, not what you are calculating. It's all about what you have been given. So let's look at a situation where you have been given enthalpy of formation data. And just as a reminder, it's not relevant here, but it will be relevant in some exam questions. The enthalpy of formation of an element is 0 kilojoules per mole. So in this equation that you've been given, the compound octane is turning into ethene and hexane. And this is the enthalpy change for the reaction that we need to calculate. Now we've been given enthalpy of formation data, and so this is when you make a compound from its elements. And so what's going to go down at the bottom here are the elements. And these elements are going to turn into octane, and they're also going to turn into ethene and hexane. We can do better than just saying that they are elements. We can say that we need 8 carbon atoms and that we need 9 hydrogen molecules. And those are the more specific elements. But unless you are asked to construct a cycle, you don't actually need to do it. You could just write elements, and that can help you with your calculations. So what's happening on the left-hand arrow is this is the enthalpy of formation of octane, C8H18. And this is the enthalpy of formation of ethene, added to the enthalpy of formation of hexane. And so to work out our enthalpy change for the reaction, which remember we're starting at the bottom of the blue arrow and we're finishing at the top of the blue arrow, so we need to find the alternative route. So we're going against that first arrow, so that's going to be negative, and then we're going with the second arrow, so that's going to be plus. And so the enthalpy change for this reaction is negative the enthalpy of formation of octane plus the enthalpy of formation of ethene and hexane on here. More generally, if we have got some reactants and they're turning into products and we're given enthalpy of formation data, down at the bottom will be the elements. And so the arrows from the elements always point upwards to both the reactants and the products. And so our unknown is this top one, enthalpy change for the reaction. And so the left-hand arrow, because we don't have any identities, we can just refer to this as the enthalpy of formation of the reactants. And the right-hand arrow is the enthalpy of formation of the products. And the alternative route is going to go in the exact same way as before. And so we're negative the formation of the reactants and we're positive the enthalpy of formation of the products. And so we can say that the enthalpy change for this reaction will be the sum of the enthalpy of formation of the products, take away the sum of the enthalpy of formation of the reactants. And that's useful, and that will get you a mark in an exam. And if it's a quick-fire mark that you're looking for, the enthalpy change for a reaction is the formation of the product, take away the formation of the reactants. If you've been given enthalpy of combustion data, then this changes everything, because when you burn something in a combustion reaction, you don't make elements. What you make is you make the oxidation products. And the oxidation products when hydrocarbons burn are more specifically carbon dioxide and water. And then we need to balance this. It's the same reaction, so we're still reacting octane, so we've got 8 carbons still, but this time we're making 8 CO2 and we're making 9 H2O. And when you burn things, the arrows always point downwards. That's helpful because things burn down, so in combustion the arrow goes down. And so now we have got a complete Hess cycle, just as before. We are trying to find out the enthalpy change starting at the bottom of that arrow and going to the top of it. So we're going to go down this arrow, which is going in the correct direction, and then we're going to get over to here and we're going to be going against this arrow, so this is going to be the negative. And so the enthalpy change for our reaction will be, we're going with this arrow, so it will be the positive of the enthalpy change of combustion of octane, and then we're going against this arrow, so we'll be taking away these two enthalpy changes added together, as you can see from this relationship here. And again, if we consider this more generally, reactants turning into products, that's our enthalpy change. When we burn the reactants, we make the oxides. When we burn the products, we make the oxides. And so if we move this way around, what we're saying is the enthalpy change for any reaction is the sum of the enthalpy of combustion of the reactants, take away the sum of the enthalpy of combustion of the products, or abbreviated slightly, it's the combustion of the reactants, take away the combustion of the products. And again, this will definitely get you marks, 1 mark, for stating that relationship in an exam. And I know I've already said this, but I said I'd repeat it. It doesn't matter what enthalpy change you are calculating. All that matters is the data that you are given to calculate it with. Why do I keep saying it like that? Well, for questions like this. If you are asked to calculate an enthalpy of formation value using an enthalpy of combustion set of data, then things get really confusing because you've got two complicated sounding terms. My advice in this instance, obviously it'd be written slightly more eloquently, would be to get rid of the concept of what you are trying to calculate. We're trying to calculate an enthalpy of formation, but that doesn't matter. That doesn't affect the process that we go through. Rather than thinking of it as enthalpy of formation, think of it as an enthalpy change for the reaction, like we've been doing so far. So I've written enthalpy of formation above the blue arrow. Let's change it to enthalpy of reaction, because all that matters is the enthalpy change that we are given to use to calculate them with. So suppose the unlikely thing has happened and we've been asked to finish this Hess cycle off. So let's do that. We're burning things, so the arrows are going downwards. And we have got one carbon. So we're going to make one carbon dioxide. We've got two hydrogen, so we're going to make two water molecules. And we haven't been given enough oxygen up at the beginning because in methanol there is only one oxygen. We're calculating the enthalpy of formation of methanol, and here are all the elements that make methanol up, but we don't have enough oxygen to make all of this water and carbon dioxide, so we need 3/2 oxygen to add to it, and we need the same on the left hand side as well, 1.5 oxygen gas to add in here. So this is now a complete Hess cycle. Now we need to put the data in, because this is where it gets complicated, because this arrow on the left hand side is the enthalpy of combustion of the reactants, but we need to do a bit better than that, because what it actually is the enthalpy of combustion of carbon and the enthalpy of combustion of hydrogen times by 2, because there is a number 2 here, which means that we're not burning 1 mole of hydrogen, we're burning 2. And the products are easier. This is just simply the enthalpy of combustion of methanol. And so our actual calculation, the enthalpy change for this reaction, is the enthalpy change of combustion for the reactants, take away the enthalpy change of combustion of the products, which is the combustion of the reactants is 1 times by carbon and 2 times by hydrogen. So you'd be given some data and you would have to do the multiplying for the hydrogen, and then you'd add those two numbers together and you'd take away whatever the value is for methanol times by 1. And so on this occasion there's just one multiple that you need to do, but the two on the left hand side would need to be added together before you get your final answer. So remember, it doesn't matter what we're calculating, it just matters the data that we've been given. And I think it's just worth reiterating that bit about multiples. So if we're burning 3 methane molecules, in our calculation we will need to multiply the enthalpy change of methane by 3, whatever that number is. That's not important right now. And similarly, if we are working with enthalpy of formation and we are making 2 moles of carbon dioxide, then we'll need to take the enthalpy of formation of carbon dioxide and we'll need to double it and use that quantity in our Hess cycle. I just want to show you right now that the principles that we've been working with in Hess cycles can be applied in the exact same way to enthalpy diagrams, with the slight exception that they're sort of at 45 degrees. All the angles are either up or down. Otherwise, the principles are exactly the same. So if we start here, and I won't complicate things by giving any chemical names, we'll just talk about the reactants and the products and some intermediate that is made along the way and then used up again. Now, if the reactants, when they turn into the intermediate, this requires 150 kilojoules per mole, and then the intermediates, when they turn into the reactants, that releases 60 kilojoules per mole, we can work out what the enthalpy change for this reaction will be. And to do that, it's the exact same principle. We're starting at the bottom of this arrow here, and we're going to the top. And so instead of doing that step, we have to go up to the intermediate. We're going with that arrow, and then we're going down from the intermediate to the products, and again we're going with that arrow. So we're adding these two numbers together. So the enthalpy change for this reaction is plus 150 plus minus 60. In other words, minus 60. And so the final value is 90 kilojoules per mole, plus 90 kilojoules per mole. If you don't put that plus in, they will assume it's there. So that will be fine if it's a positive value, but not if it should be exothermic. And so what you'll notice about this diagram is that positive values always point upwards for the endothermic because the chemicals are gaining enthalpy, and the exothermic reaction arrows always point downwards. So I knew what my value was going to be before I wrote it, which is why the reactants are below the products, because this is a positive number. We're going to move on to our final aspect of this video, which is the concept of the mean bond enthalpy, sometimes referred to as bond energy. I might slip into that by mistake. And also, this can be known as the bond dissociation enthalpy. So all three terms can be used interchangeably. So I'm going to try and prioritise the use of the term mean bond enthalpy. And it's got the symbol capital B. And mean bond enthalpy is defined as the energy required to break a covalent bond. And so two important emphasis points there. It is the breaking of a bond, and it is a covalent bond that is being broken. These values are always positive, and the reason is that bond breaking is endothermic. And in addition to that, these values, as the name describes, are average values. And what that means is you take the bond enthalpy of a carbon to hydrogen bond in an alcohol, say, and in an alkene, and in an alkane, and all the other different families of chemicals that have carbon to hydrogen bonds in, and you average that bond enthalpy across all the different types of chemical and all the different lengths of chain, and you get an average value for the strength of a carbon to hydrogen bond. And you can see the value here is plus 413 kilojoules per mole. And the strength of the bond will obviously influence the bond energy. It will influence the energy required to break it. If we compare a carbon to carbon single bond, the bond enthalpy is 348 kilojoules per mole. And if we compare this to a carbon to carbon double bond, the bond enthalpy is 612 kilojoules per mole on average. And what I should say is that these are always positive values. In other words, if you have got a hydrogen to hydrogen bond and we're breaking it, we're going to end up making two single hydrogen atoms. These will be in the gaseous state. And in fact, part of this bond enthalpy is all of the species have got to be in the gaseous state. And that makes sense if you consider the fact that we are breaking a covalent bond. And if we're putting in enough energy to break that bond, there's definitely enough energy to overcome the intermolecular forces between the covalent molecules to make it turn into a vapour. One last thing to mention on this is that the bond enthalpy of the hydrogen to hydrogen single bond is plus 436 kilojoules per mole. So that's the energy that has to go in to break that bond. If we were to make that bond, then the bond enthalpy is flipped and energy is released this time when we're making new bonds, and we would be releasing exactly the same amount of energy to the surroundings as would be required to go in to break that bond, minus 436. We're going to take a look now at how you would do a bond energy calculation. And I've got here an equation shown in full displayed format, which is definitely the most easy way to approach bond energy calculations, because showing an equation in molecular formula, it would look as I've shown here in red. You might have remembered this from GCSE level, that the enthalpy change for a reaction is found by taking the sum of all of the bond energies of the bonds that are being broken and subtracting from it the bond energy of all of the bonds that are being made. Or, to put it in a slightly more useful A-level context, the enthalpy change is the sum of the bond energies of the reactants, take away the sum of the bond energies of the products. So, to approach that question here, our enthalpy change for this reaction is the sum of all the bond energies of the reactant, so let's add all of those together. We have got 1, 2, 3, 4, 5 carbon to carbon single bonds. We have got 10 carbon to hydrogen single bonds, and we've got 1 carbon to carbon double bond, and that's all in the cyclohexene, and then we've got 1 hydrogen to hydrogen single bond. So we would need to add all of those bond energies together, and then we would subtract from that 6 times the carbon to carbon single bond enthalpy, and 12 times by the carbon to hydrogen single bond enthalpy. And we would get our final answer, and it would be in kilojoules per mole. Having said all of that, what we can actually do with this situation is make it a whole lot simpler by looking at which bonds are actually changing in this chemical reaction. So on the left-hand side in the reactants, we've got 5 carbon to carbon single bonds. On the right-hand side in the products, we've got 6. So in fact, the only thing that's changed is we have gained a carbon to carbon single bond. In addition to that, what we have lost from the reactants is we have lost this carbon to carbon double bond and the hydrogen single bond. We've also gained in the products this carbon to hydrogen single bond and this carbon to hydrogen single bond. So in fact, the only bonds that are breaking overall in the reactants are these 2 bonds listed here. And in the products, all we're doing is making 1 carbon to carbon single bond and 2 carbon to hydrogen single bonds. And so this calculation is much simpler than before, because all we're doing is adding together 2 numbers for the bond enthalpies of the reactants and then adding together 3 numbers for the bond enthalpy of the products. And so what we're getting is a simplified picture because we're looking at the overall change and we're adding together fewer numbers. We can use a Hess cycle to explore the origin of that calculation. And if we take our standard situation of the reactants turning into products, if we're using bond enthalpy data, what we will be doing is breaking the reactants apart into the gaseous atoms. And so our Hess cycle will have the arrows pointing downwards because we're turning the products into the gaseous atoms, or we're turning the reactants into the gaseous atoms. And so this arrow on the right hand side is equal to the sum of the bond energies of the products, and this arrow on the left hand side will be equal to the sum of the bond enthalpies of the reactants. And so when we're calculating the enthalpy change for this reaction, we're starting at the bottom of the arrow and going to the top, but we're doing it through the alternative route. So we're going with the bond energy of the reactants arrow, so that will be positive, but we're going against the bond enthalpies of the products arrow, so that needs to be subtracted. And so overall, the enthalpy change for our reaction is the sum of the bond energies of the reactants, take away the sum of the bond energies of the products. Bond enthalpy data can be used to explain the pattern in enthalpy of combustion of the alkanes as the alkane chain gets longer. If you were to plot a graph of the enthalpy of combustion against the number of carbon atoms in an alkane molecule for the straight chain alkanes, you will get a straight line graph. And I know that I haven't put any numbers on this graph, but the fact that it's a straight line means that the enthalpy change of combustion changes by the same amount for each extra carbon atom that we add to the chain. And this makes sense because for each extra carbon atom that you add into the chain, we add an extra 2 hydrogen as well, and we add an extra 2 carbon to hydrogen bonds. and we also add an extra carbon-to-carbon bond for the bond between the new carbon and the last one in the chain, as was before. So we've added 3 additional bonds, and when you burn this alkane, that means there's 3 additional bonds to be broken. When that extra carbon atom burns, we will produce an extra carbon dioxide molecule, and we will also produce an extra water molecule. And so as a result of that, we are making an extra 2 oxygen to hydrogen single bonds, and we're making an extra 2 carbon to oxygen double bonds. So once again, we're making an additional number of bonds. And so this is why you see the linear pattern for the enthalpy of combustion, because we are having to break the same number of additional bonds and we are forming the same number of additional bonds. As with any comparison between theory and experiment, it doesn't work 100% perfectly. It is not the precise same increase each time. And if you use bond enthalpy data, it would lead you to believe that it was. The reason for this is quite simply that these are mean bond enthalpy values. And so they don't take account of the type of molecule in question for this particular situation. And so if you're given an exam question where they ask you why might the value that you've calculated using bond enthalpy data be slightly different to what you might find in an experiment, then the most likely answer in this situation is the fact that you are using mean bond enthalpy values and not personalizing it towards the molecule in the question. This is assuming that you are not allowed to mention heat loss to the surroundings, because that is definitely the number one cause of differences between theory and experiment. But if they're asking you about bond enthalpy data, they will normally say, other than heat loss to the surroundings, what is the reason for the difference between theory and experiment? And that will be when they're talking about mean bond enthalpy values being used. And so, to finish off this video, when you're calculating the enthalpy change for a reaction, it doesn't matter what type of enthalpy change you are calculating. All that matters is the type of data that you have been given to do your calculation. And so if you've been given enthalpy of formation data, you will be calculating the enthalpy of formation of the products, take away the enthalpy of formation of the reactants. If you have been presented with enthalpy of combustion data, you will be doing your calculation by taking the enthalpy change of combustion of the reactants and subtracting from it the enthalpy change of combustion of the products. And last of all, if you have been given mean bond enthalpy data, you will take the bond enthalpies of the reactants and subtract from it the bond enthalpies of the products in order to find the enthalpy change for this reaction. Okay, that's everything for this first video about energetics. There will be a second shorter video about measuring enthalpy changes during experiments, released very, very soon. Thanks for listening. I hope it was useful. Bye-bye.